Welcome back, everybody, to day one of the VM Workshop 2021. Our next session is Brian Wade. He'll be giving us an update on ZVM performance. So over to you, Brian.
Okay, Bill, thank you. Today is June 10th, 2021, and my name is Brian Wade, and here is the ZVM 7.2 performance highlights for the first quarter SPE stack that we shipped. We put out a number of PTFs in the first quarter, and I just want to take a few minutes, maybe 15 to 20, to take you through some of the performance highlights of that SPE stack. In the couple of minutes after that, I want to tell you a little bit about how we cope with the idea that the computer never really does the same thing twice. And that's not because of an accident. It's because things naturally vary, and we as performance specialists encounter that. And I want to show you a little bit about how it is we cope with that. So if you're the kind of person who likes to have just one chart, perhaps to show your manager or your teammates what you learned in the presentation, I included this agenda chart, not only with the topics, but what your takeaways would be over there on the right-hand side. Regression results were great. You can feel confident about the 4 terabyte line item. We exploited high-performance Vicon I/O in dumps, snap dump, for example, and we took an awful lot of elapsed time out of dumping. I'm going to tell you a little bit about that. We made an improvement. This was a joint project between Bubbling In and Endicott. We made an improvement in how certain instruction sims are done related to PCIe, and that resulted in some very nice improvements in transaction response time for the workload we used. We made some improvements in the ZVM TCP/IP stack for exploiting outboard validation of client certificates, and that took CPU time per connection down somewhat. And then regarding run variation, we're coping pretty well, and I'll show you some ways that we accomplished that. One of the things I like to explain when we get into the notion of how well the next release does, or how well the next SPE stack does, is to talk about something that's called regression. We generate a regression report card for our stacks every time we ship an SPE stack or a release. The word regression means that we take workloads that ran on release n-1. They don't intentionally exploit any new function in release n, and we just run them again to check for parity. We might get some coincidental improvement because we improved some core function, but we're at least looking for parity. Our purpose here is to try to find out or forecast what your experience might be if you go from, say, 6.4 to 7.1, or 7.1 to 7.2, or 7.2 to the spring 21 stack. That's what we're looking for. We don't want you to find those things. We want to find them in our what we call regression workloads. We run about 70 regression measurements for every bundle, and they intend to exercise the system in various ways. They exercise paging, and they exercise virtual I/O, and they exercise CPU management, blah blah blah. And for every one of those workloads, we collect 2 really important measures. We collect application work accomplished per unit of time. That's called external transaction rate, or ETR. And we collect a related number called internal transaction rate, or ITR, which is the formal ETR divided by the percent of the CPU resource that's been consumed. This is ITR is a measure of efficiency. And then we calculate ratios, as I've shown here in the 3rd bullet. We calculate the new ETR divided by the old, and the new ITR divided by the old, and we look for parity. So what I did was I put over here on the right-hand side of the chart a graph of just our ITRs, CPU efficiency, for all of those 70 workloads, and you'll see that a great number of those ratios are right around 1. I call this a big success for an SPE stack or for a new release, that workloads that didn't exploit anything did just fine. We didn't accidentally debilitate something, and that's what we're looking for. Now, you might wonder what is going on right here. We had 2 workloads that experienced a nice ITR jump. I told you that sometimes if we improve a core function, we end up with improvements in these regression workloads. And what happened here is we have 2 workloads that are very, very heavily exercise guest page instantiation and guest page release. The 4 terabyte line item in this SPE stack improved that code path, and because these workloads beat on that particular path, they showed a nice improvement. So what we have here in this part of the chart is over the whole set of measurements, what were the ETRRs and the ITRRs? And you can see that these are very close to 1 with small standard deviations. And the smallest ratio was really about 0.97. I feel very happy when our set of regression workloads comes out this way. And I'm delighted to tell you that these are my team members who did these things. Billy Gouger looks after CMS regression. Dave Spencer has his hands in a lot of different things. Xenia works on SSL and connectivity kind of regression, and so does Dave Werbowski, and I try to keep them all going the same direction. Every once in a while I get lucky and actually get a line item too, but as Bill will tell you, as you grow in this discipline, you don't get to get your hands dirty quite as much. You end up leading other people. Okay, so let's move on and talk about the 4 terabyte line item. You can use 4 terabytes of central in your APAR now. That's double the previous amount. I used to work with a guy who would scoff at these scaling or capacity improvement kind of line items we would do. This engineer who was somewhat naive would say things like, well, of course you can support more processors. All you do is just change the size of your arrays and recompile, and you've got support for more processors. Or you change the size of your arrays and in your control blocks and you've got support for more memory. This was a very, very naive sort of view about what it means to be able to grow. Just because you can use all those processors, just because you can address all that memory, doesn't necessarily mean that you can claim that you can support it. You have to be able to scale in a manner that makes sense for the workloads you run, and in particular, you need to be able to scale in a way that makes sense given what we've already told clients about the hardware's ability to scale. So we run a variety of workloads. We run workloads that press on the caches very lightly. Some press on the caches very heavily. Some are memory constrained, some are memory rich, and we typically run an arc of them when we're trying to evaluate scaling behavior. Well, over here on the right-hand side, I've illustrated the scaling behavior for ITR for a workload that we call P-touch, which is a memory constrained, memory overcommitted paging kind of workload. And you'll notice that I drew 2 graphs here. I drew the scaling behavior of the P-touch workload on ITR, and I also drew this line called CAF, C-A-F. That stands for capacity adjustment factors. The hardware contains, and you can extract these by issuing the Stacy instruction, contains scaling coefficients that the hardware engineers found when they ran their reference workloads in larger and larger amounts as they scaled up. One of the ways we can evaluate whether ZVM scaled correctly is to compare our scaling curves to the CAF curves. Now, we won't always match. Sometimes we'll be a little better, as we were here in P-touch, and sometimes we'll be a little worse. But the point here is that we want to make sure that we don't have any really bad problems. For example, we get a little bigger and then the curve really rolls off like this. That would be an example of failure to scale. I'm very happy with the scaling behavior of the 4 terabyte line item, and I put the net right here in green. If the Z hardware can be expected to scale the client's workload, ZVM can also be expected to scale it. The ZVM control program is not a barrier to scaling. It's between your workload and the hardware. Dave, Xenia, and I all together worked on this, and I was very happy with the result. Now, another line item that we shipped in the first quarter stack was this notion of exploiting high-performance FICON I/O for dumps. This was due largely to my longtime friend Bob Rogers, who came in and said, we could probably do this. He quoted his own friend, Harry Udenfriend, as saying, you really ought to be looking at high performance FICON for lots of different things, because we know that it can do I/O a lot faster than the old command mode sort of I/O. So we changed SnapDump. Bob and John Rule worked on this together. They changed SnapDump and Friends to use transport mode I/O instead of ordinary command mode I/O. And what we looked for was whether we could take I/O time out of the dumping process. We didn't really expect to take any CPU time out of the dumping, but we did expect to take I/O time, and it came out almost exactly the way Harry said that it would. The I/O time in the dump was cut by about half, and in our particular measurement, the elapsed time of the dump was cut by about 45%. I need to give Bill Gouger some credit here. He did all the runs, threw the numbers at me, and let me figure out whether it worked okay. But Bill was able to set up a workload that he could bring up, and it would produce about the same memory footprint every time. So as we did a dump and another and so on to evaluate the line item, we had the same basic amount of stuff to be dumped. So I was very pleased with what happened here with dumping, and I think you'll be pleased too. Of course, we don't want you to have to dump, but when you do, we'd at least like it to proceed in a fairly fast way. Another PTF that we shipped in the first quarter was this thing regarding improvement of how we do instruction simulation for an instruction that's related to using the PCIe adapter. We found places in the control program where it was possible for us to skip talking to the real hardware, even though the guest had done something to its virtual PCIe function. I talked more about this in the performance report chapter, which is linked down here. I think those of you who've been around virtualization for a while know that when the guest does something that's a priv op, we take an intercept, and the control program has to do something to satisfy what the guest was trying to accomplish. It has to make the guest think that his priv op actually did what he intended for it to do. And usually the control program talks to some hardware on the guest's behalf. We were able to find things that we could avoid doing. We could avoid talking to the hardware in some cases, even though the guest had sent us a priv op. And that resulted in a nice decrease in transaction response time and decreased steal time. And this was admittedly a workload that was intense on the use of the PCIe adapter. This was one of my first experiences working with analysts in another lab to get a chapter done for the performance report. And I want to thank Mark and Thorsten for their terrific contributions as we did this. They would do the runs and send me the Monwrite data, and I would look at them, and it was a very, very cooperative, very friendly, very nice environment. And I was delighted to work on the line item. So nice work there by Mark and Thorsten. One of the other things that we did was we changed the TCP/IP stack so that it could offload the validation of client certificates to what we call an external validation server. And Xenia Katashow did the measurements here for us. We looked for whether we could get rid of some CPU time as a CPU time that was associated with establishing a new connection. So Xenia has this workload that kind of puts the stack into a frenzy. It just continues to allocate and allocate and allocate and allocate new connections until it has about 600 of them. She does this in a very paced, very staged way so that she can keep track of the amount of CPU time that it takes to add one more connection as a function of the number of connections that already exist. We would expect some growth in that number as we move toward the right side because the stack is juggling more control blocks. Maybe there's some kind of longer list search in there, or we wouldn't expect it to be flat. And what we found was that she was able to take CPU time out of measurement. She reduced the CPU time spent in the stack by a significant amount, and she reduced she changed the time in the basic stack just a small amount. There was a little bit of growth there, but that was more than offset by the drop in the amount of CPU time used in the SSL servers. So nice report from Xenia, and it was a pleasure to work with her on this project. I want to talk to you about a couple of what I call honorable mentions. These are line items that we did not measure, but nonetheless shipped in the first quarter, and I think this would be nice to tell you folks about. John Rule and Bob Rogers did some work on dump load, and this went under the line item named Fast Dump Distiller. They wanted to try to improve the amount of time that it takes to run dump load. So as they were reading the spool file, they skipped over parts of the spool file that represented data structures they felt didn't need to land on the A disk. And by doing that, they reduced the time needed to get the essential parts of the dump out. Now, when they're doing this, they leave the dump spool file there. So if you have to go back and load it again and get everything out of spool, you can go do that. The improvement that they got in the dump load process varies a lot according to the character of the dump. How much of it is stuff that they can leave versus how much of it is things that they want to go ahead and read to the A disk. And for that reason, we didn't measure it. The results will be, for you, will be consistent with the mixture of data structures that are in your own dump. The other thing we shipped in the first quarter was something we called architecture support for a new machine mode, ZXC, which allows Z architecture instructions to be run in an XC mode virtual machine. I personally was delighted that they did this line item, because the way I do my work every day is I live on CMS, and I use PerfKit, and I also use our code versioning system, our code control library, which depends very heavily on SFS directories, dirt control directories in data spaces. Those of you who remember that technology from way back now, actually, probably remember that that required XC mode. But when PerfKit started exploiting Z architecture, all of a sudden you couldn't run it in an XC mode machine anymore, and my life got harder because my SFS performance went down. With the addition of these two APARs, one for CP and one for CMS, I got my life back. My CMS session is much better now because I can use those two technologies concurrently. I can run PerfKit, and I can still exploit SFS directories in data spaces, dirt control directories in data spaces. So if you're using those, that'll be nice for you too. Okay, so we have a few minutes remaining, so I want to talk with you about the notion of run variation. As measurement specialists, we know that if we go into the lab 2 times and we run the very same experiment, we don't get the same answer each time. It's off a little bit. I used to work with an analyst who had a catchphrase. He would say to me, "Brian, if you didn't change anything, why did you run it again?" And I always laughed about that, because it showed me that analyst was not quite in tune with the idea that there's natural fluctuation in everything. One of the things we used to carry in our regression evaluations was we would say, if it's within X% of the previous release, I'm not going to tell you what X is, but if it was within X% of how the previous release performed, we would say it was okay, and we would brush it off to run variation. We don't do that as much anymore. Rather, if we notice variation, we have ways that we can study it. And I'm going to tell you about one of the ways that one of our analysts studied this. So you have to be on the lookout for variation. You have to cope with it when it happens. And it turns out that there are techniques from mathematics that we can use that'll help us to see the difference between it just naturally varied and we changed something, and that caused it to vary. And we're going to talk a little bit about those things. So what I have here is a chart that says we can be misled. And this is a place where I probably should have used presentation mode, because these bullets all fly in at different times, but that's okay, we'll just cope. Let's say we have a job called My Job, and we ran it on ZVM 7.1, and we ran it on 7.2, and we got these 2 answers for ITR. And it looks like 7.2 is a little better than 7.1. You might walk out of this and report to your manager that, 7.2 got 4% better, but that wouldn't really be a responsible thing to do. It might be run variation, or maybe there was a setup problem, you don't know what. So you try to go back to the lab, and maybe we'll run it a few times and see if we can find out what happened. And that's what is depicted over here on the right-hand side. You can see the first trial, 7.2 is a little better than 7.1, but as we did 5 trials of each experiment, you can see that these things crossed over, right? There's some vibration in the 7.1 result, and there's some vibration in the 7.2 result. And what we'd like to know is whether we can say anything meaningful about the comparison rather of 7.2 to 7.1. So your first reflex might be, well, we'll just take the average. We'll take the average of the 7.1 results, and we'll take the average of the 7.2 results, and we'll compare those, and we'll claim that the change is 1.2%. So that's a different answer from 4, but it turns out that that's also wrong. You can use a statistical technique, which goes by a number of different names. The most popular name is students T, to use the standard deviation in these sample sets to tell you whether you can conclude anything about the difference between the behavior of 7.2 and the behavior of 7.1. And when you run a t-test over these 2 sample sets, what you find out is something called the confidence level, or the CL, comes out to be 0. And what that means is that the difference between these experiments is not meaningful. Look at how much we learned compared to this. 7.2 is not 4% better. It's indeterminate. This runs up against the gut of something that we learn as babies, that 2 things are either the same or they're different. They're either the same or they're different. As performance specialists, we need to keep in mind that those are not the two alternatives. The two alternatives are we know nothing, or with some percent confidence level, we can say that they're different. And it's very difficult to confront that first emotionally, but it turns out that that is in fact the way we have to run our lives as performance specialists. So let's take a look at another scenario where once again we ran 7.2 and we ran 7.1 on our workload called My Job, and it looks like 7.2 was 4% better. So having been a little more well informed, we go back to the laboratory and we say, okay, we're going to run 7.2 5 times and we're going to run 7.1 5 times, and we got these curves instead. And when you look at this with your eye, you say, well, look, 7.2 kind of hovers above the 7.1 line almost all the time. We have some hope here, where on the previous chart, owing to all that crossing, we don't have a lot of hope. So you calculate the means of these two sample sets and you say, well, maybe 7.2 is 3.2% better. But what did the t-test tell you? The t-test, when we did it, students T, said that there is 99% chance that the difference in these means something. And that causes us to think very differently about the behavior of 7.2 compared to 7.1 than this did, and also than the confidence level 0 on the previous chart. So you might think, oh my gosh, what about all this lab time that we're using doing all these measurements? How can we afford a 5x expansion in our machine time to get reliable measurements that are going to make Brian happy? Well, it turns out you don't have to do that. Maybe your run takes only 10 minutes and it's automated, so you can use night shift time and come in the morning and see all your results. But maybe it's more like this. Maybe it's more like that the experiment runs for 10 minutes, but the monitor sample interval is set for 1-minute intervals. A naive person would say that's one experiment that ran 10 minutes. But it's not. It's really 10 experiments that ran one after another at 1-minute intervals. So if you can collect an ETR at every monitor sample interval and do calculations for every monitor sample interval, all of a sudden you have the 10 samples that you need, and you didn't expand your measurement time at all. And that's something that we need to keep in mind. So let's take a look at our IO analyst and networking analyst. Dave Werbowski is this guy's name. He's been working with us in performance for a couple of years now. I'm very pleased with his progress in learning our discipline. He has runs that try to evaluate the behavior of VM networking, like vSwitch and dedicated OSA and all that kind of thing. And his runs are very heavily automated. They run overnight. Nobody touches them. When he comes in, he gets an email that tells how everything went. He really did a nice job on automation. Networking is one of the places where there's the most fluctuation. So what he does is he collects a number of trials of each one. In this case, he did, say, n trials of the 4Q20 stack and then n of the first quarter stack. And then he uses students T to check whether the difference of the means is statistically significant. And he's looking for a 95% clip level, which is about the clip level you would use to figure out whether the vaccination worked, right? So this is a fairly stringent standard. If he's got his significance, then he'll investigate it got better or worse. But below confidence level 95% in the t-test, it's just not worth looking at. Just move on, and this helps him not to be misled by ordinary run variation. So I'm at about 25 minutes. They allocated me a half of an hour, so I came in a few minutes early. This is the summary, the bullets. The regression performance on the first quarter stack is fine. I didn't see anything wrong with it. You should be able to use a 4 terabyte partition. I think it's going to scale okay for you. The dumps, we got nice improvement in the IO time there. I think you'll be pleased with that if you end up having to collect dumps. If you're using PCI workloads, you should get some improvement there in your transaction response time, and you should see some result in, some reduction in steal time. And if you're doing external client certificate validation, you ought to see some reduction in CPU consumption in the SSL machines. So again, I'm Brian Wade from VM Performance, and this is the first quarter update. Bill, I'll give it back to you.
Thank you very much, Brian.
You're welcome. It was my pleasure. I want to thank the committee for accepting my abstract.